Hey guys, welcome back to the shop. When I was at Blade Show a little bit ago, I picked up a piece of MagnaCut steel from the folks at New Jersey Steel Baron at their booth there at the show. This cost about 30 bucks, I believe, on their store. And we're gonna test it out. We're gonna make a couple of knives from it. But I'm gonna do a little bit of explanation on the front end in this video. Don't go anywhere. I'm gonna put a piece of this in the forge and we're gonna make a couple of knives. Some people don't like stainless steel. A lot of you probably don't like stainless steel, and I totally understand. Stainless steel has not been my preferred steel, and it's not probably going to be my preferred steel. Having said that, I have had multiple people ask me about knives in stainless steel and MagnaCut specifically. I do think there are places and times for stainless steel blade or knife applications, and probably the most serious of those would be in a wet or even specifically saltwater environment. But anytime you have excessive and continual moisture, you might consider a stainless steel just because of the susceptibility of high carbon steel to corrosion in that kind of an environment. I can't really imagine using a high carbon steel blade in a saltwater environment, for example, where it's continually exposed to that kind of corrosive moisture. Obviously, back in the day when there was no stainless steel, that's what people used and they managed, right? It worked. I've also had people ask me about fillet knives specifically, and I think that should probably be made from a stainless steel. Now, I've worked with a couple of different stainless steels in the past, specifically AEBL and S35VN. Both of these steels do not require a cryogenic treatment within the heat treating process. They do require a sub-zero process, and that is accomplished with a dry ice slurry without the need for liquid nitrogen to attain the cryogenic temperatures. From what I've read and researched on MagnaCut, it doesn't necessarily even require a sub-zero treatment in the heat treat process. There are different ways to accomplish the finished hardness and properties of this steel from what I've seen, and that has to do with different austenitizing temperatures and the corresponding tempering temperatures and this kind of thing. Like I said a minute ago, I'm going to forge part of this. We're going to cut it in half, and I'm going to forge a blade, and I'm also going to do a stock removal blade. One of the drawbacks with stainless steel is that if you're going to forge it, it will then be air hardened and you're not going to be able to drill holes in it. So I'm going to do a hidden tang knife for the forged knife. A lot of people think you can't forge stainless steel, and there's simply no logical or metallurgical reason why that is true. In fact, this piece of steel has been forged. After the steel was made, it was hot rolled into this particular stock thickness, which is a form of forging. There's no reason why we can't do a little bit more forging before we heat treat the steel to achieve the hardness and durability we're after to make a good knife. Yes, it could be damaged through forging as any steel, and yes, there's going to be tighter parameters to the temperatures, for example, that we can effectively and safely forge it at, but there's no reason it can't be forged. And there's other people that hold to this opinion as well, including the designer of this steel, Dr. Laren Thomas, which I'm sure many of you are familiar with. So, having said all that, to sort of set the stage for the thought process behind this project, I'm going to cut this in half, and we're going to make a couple of knives to test out MagnaCut and see what I think of this newer steel. There is our forged MagnaCut blade. And yes, the tang is tapered. I don't need that to harden really. But the rest of this is pretty much the same thickness. And that will allow the aluminum plates that we're going to quench this with to contact the surface and draw away the heat quickly to harden the steel. So let's get this cleaned up on the grinder just a little bit. But this demonstrates one reason why you might want to forge stainless steel or any steel, but that is a lot less wasted material. Instead of having to cut away this material or what have you, it's been forged out. And I guess especially with a steel that costs as much as this does, that could be a important consideration. All right, there's our forged MagnaCut blade, and there's our nice little stock removal MagnaCut blade. So I need to go look up the heat treat protocol, and we'll get these heat treated. Probably one of the most unique things about the steel MagnaCut is that it was invented or developed by a professional metallurgist who grew up with a professional bladesmith as a dad. Larrin Thomas created this steel, and he understands some things about knife steel, but he also provides tests and parameters for heat treating his steel. So with the provided heat treat protocol, we've got a pretty middle of the road heat treat for this. Now there's different things you can do to achieve higher hardness and sort of within a certain range on this steel. What I'm going for is sort of a middle of the road type heat treat from Larrin Thomas's protocol, the actual data sheet for this steel. And he's done the testing on it in knife blade sized coupons or pieces of steel, which I think is relevant because there is a lot of heat treat information out there that's sort of more geared towards industrial type application, and so a minimum cross section of like 1 inch or something to that effect. But these are on knife blade sized pieces of steel. So we've got a 2050 degree austenitizing temperature and a 350 degree tempering temperature, and the target hardness is 61.5 Rockwell hardness on the C scale, which is right around the hardness of most of my carbon steel knives. Obviously the properties are going to be significantly different on this MagnaCut, but I want to have a reasonable sharpenability, which is going to be one of the biggest problems potentially with MagnaCut being a high alloy steel, being a stainless steel, which is one of the reasons why a lot of people don't like stainless steels. But you can't have everything in life. So a corrosion resistant, good corrosion resistance, a decent hardness, but not something screaming hard that it's going to be too hard to put an edge on out in the field. And then, you know, the toughness, the higher toughness than most stainless steels. In fact, that was the main goal from what I've read with Larrin Thomas developing the steel, was a tougher stainless steel than, you know, most other stainless steels that are out there. Anyway, that's what we're gonna do. So I'm gonna heat up my large kiln, even though it's much larger than we need. Inside for 2 little blades, it's a 240 volt, and it shouldn't take quite as long to heat up to this high temperature. My big kiln does not go to 2050 degrees. Apparently only goes to 2000. So let's try the little one. It's going to take a lot longer to heat up, but if it actually gets to the temperature, that's what's important. As I mentioned, I have heat treated stainless steel in the past in that even heat kiln, so I'm sure it'll be just fine, but it's going to take longer because it's only 120 volt. So that's something to keep into consideration when you're buying a kiln if you're going to do stainless steel. So one of the biggest considerations with stainless steel, if you're going to heat treat it, since it has such a necessarily high austenitizing temperature, you have to protect the steel from atmosphere. And so if I just put this in the kiln and heat it up to 2050 degrees and then leave it in there for the necessary soak time of, gotta go double check that, 20 minutes, I'm pretty sure, we're gonna have a serious decarb issue. We're gonna ruin a lot of this steel, and maybe to the extent where we can't even get a good knife out of it. So we have to protect it from atmosphere, keep the oxygen off of it. And the simplest way to do it for most people is with a high temperature stainless steel foil packet. The austenitizing temperature is necessary because of the very high alloy content. The chromium, any stainless steel is going to have a minimum of like 12-13% chromium and goes up to somewhere around 18%, I believe. But any alloy like that, including things like vanadium, molybdenum, tungsten, these all significantly slow down the movement of carbon within the structure of the steel, going into solution as the term goes. And so it's necessary to heat the steel up much higher than a carbon steel to overcome that, so that the carbon can go into solution and you can actually achieve appropriate hardness levels for the steel. So this is some stainless steel foil, and it's also important to double check the temperature rating on your stainless steel foil. This is rated for up to 2200 degrees Fahrenheit. So we should be good to go on that, but not all stainless steel foils go up to that temperature. So be cognizant of that.
get a turn of anything.
Why are you over there? Maybe I was
You're gonna have me that giant
This
one.
is a chipotle seasoning. Char, will you run out and grab the big spatula off of the barbecue? It's on the right-hand side. Pretty please. I gotta turn this one real fast. It's gonna get done super fast.
He's so small, and the egg's so
You know what we need is like a lid to put over these so that the heat melts the cheese better.
Hey, Dad?
Yeah.
Is it okay if I don't have that type of cheese on my burger?
Well, that's all I got, so you can pick one without cheese on it.
I want one without cheese.
Okay, and then I got some hot dogs too.
Look, Dad. The duck.
Is that why you got them?
Good job. Yeah, I saw that. Good resistance. It was good self-control. You looked right at those hot dogs and you thought about it and you looked the other way.
All right, well, both of these suckers came out of the quench, or I should say out of the freezer, with pretty good warp in them. The forged one more than the stock removal. But this is the third time I've had them out of the temper real quick. So put some pressure on it at tempering temperature. That was the wrong way. Get them straightened out. This trick here works with some steels. I'm not super familiar with it, but being able to put some tension on it while it's still at tempering temperature gives you the best potential option for straightening it, if you're going to straighten it. Just got my hardness tester set up on a better base here, so I'm just checking the calibration. Made a minor adjustment here. Oh yeah, money. All right, let's go test the hardness of those blades. This finish might be just a tad rough, but I'm gonna see what we can do here. Ironically, the hardness that we're actually going for is exactly that of the test block. All right, moment of truth. Oh, well, we're running at 50, almost 58. It's not what I wanted to see. Now, I'm testing just on the surface finish of the steel, which probably is not a good idea, but a couple reasons for that. I don't want to have to grind this off and sand it if at all possible, but I may do that. I want to be able to leave some of the mill or forge finish on that blade, on the flats of the blade. So this is reading at 53, which is not surprising because we forged this knife, right? So it is going to have some decarb on the outside of the steel. So this is not a accurate reading. On our first reading, we got 58 on the scale here, which is a little low, but the surface finish does affect the hardness reading. And, you know, really I should grind and sand this surface down. The only reason I'm able to even do a reading that's going to be remotely accurate on this blade in this condition is because we did have it in the atmosphere protection of the stainless steel foil. This blade right here that we forged, you're gonna have a layer of decarb, and so there's no way to get anything close to an accurate reading without removing the top layer of material. But I just want to see what this is reading at. There we go, 62. So that's the other thing about this is you got to take a few readings and see where things kind of average out. 62, 58, that puts us right in the middle, right where our target hardness is supposed to be. But these softer readings here, I'm attributing more to things like the surface finish. And you know, if we had wild problems with the heat treat, we wouldn't be getting a 62 reading on here. And if there was a minor breach in our foil, then there's probably some minor decarb, things like that, without actually grinding off the surface and really paying attention to that. Then so now we're up to 63 here. So all that to say, I don't see anything wildly out of order that would require going back and repeating the heat treat process. If I was trying to dial things in really close, I would, you know, do a little more careful prep of the steel surface, etc., different things like that. But I just want to make sure that we're, you know, in the ballpark, and by that I mean like a couple of Rockwell points at most, and that's kind of where we're falling in the middle there. So I think we have a good heat treat on these to proceed and see what we think of the steel. All right, high carbon, high alloy, a significant level of hardening just in still air compared to most steels. Not going to be able to drill through this, but I want to see if I can sphericize it, anneal it sufficiently to be able to do that. I don't think I can, but I'm going to give it a shot. Just go into a really dull red, which you can't even really see in this light. All right, we'll let that cool, and we'll see if we can even touch it with a non-carbide drill bit. I don't think I can, but we'll see. All right, we have two knives out of MagnaCut steel. Now I just want to say something real quick before we go on. The hardness testing that I did, don't do it that way. This is not meant to be a how-to by any stretch. I was just checking to see if it was hard, which I already knew it was, but I did end up grinding off some of the ricasso area prior to putting on the handle scales and cleaning that up a little bit, and did another test, and it was right in the area that we're looking for, about 60 Rockwell hardness, 61. But I also want to point out that on a good day, you're going to have, you know, a point to, I think even 2 points of variation on the same blade. A point in either direction is not uncommon, so you always take multiple readings and average them anyway. So all that to say, I'm perfectly happy with the heat treat. But we've got a couple of blades here, and this one is actually going to go to Alaska, where a good client of mine is going to put it through the paces on multiple Alaskan big game hunts and field dressing animals, everything like that. He has purchased multiple knives from me in the past and put them to work up there in the bush. So I'm excited to get his feedback on this little knife, especially since he's very familiar with the 5200 high carbon steel blades that I routinely forge and make. So that's where that's going. This one I will be putting through the test myself on specifically more like woodcraft and general use tasks. And so between the two of these and the different blade construction methods, I hope to get a pretty good feel for how this steel performs and the heat treat that we've put on it. So they're relatively different knives here. What's ironic, of course, is that this blade was actually made with less material than this one. And as I pointed out earlier, that's one of the advantages to forging a blade. I like how both of them turned out. They're both rather different knives, but I think they'll both be very useful. This one got natural micarta, canvas micarta skills on there, full flat grind, distal taper, just a nice handy little blade, nice drop point design to it for field dressing, etc. This one, a little more of a puko style with a full flat grind, once again, distal taper, and a basic but very ergonomic and comfortable and positive grip on it. I screwed up on drilling the slot out, or the, anyway, never mind that. It's still gonna be very fun to use, I think. So the next thing we need to do is actually put an edge on these. I've put the initial bevel on with the belt grinder, but we have to actually sharpen these, make a couple of sheaths, and start using them. All right, guys, we've got a couple of knives ready to go to work. Put an edge on both of these. They sharpened up pretty easily, really no difficulty there. And so I'm interested to see what the edge retention is like. I've got a nice leather sheath for both of these. This one I'm gonna strap to my belt. We're gonna start using it. I'll get some first impressions here on this steel, on this heat treat. This is the first morning that feels even remotely like fall since last winter. So I've got a piece of pine, pretty soft, and I've got a piece of hickory, not quite so soft. Not the hardest wood out there, but definitely a lot harder than your pine and spruce. And let's see what this can do here. So I wanted a heat treat that was gonna allow for ease of sharpening in the field. So not the hardest heat treat possible on this steel. And you know, something that's gonna have good edge retention. So doing some cross grain carving on this hickory here with the blade, with the edge. If anything's gonna break down an edge, this would be one thing. All right, well, to be completely honest, I'm not really happy with this so far. I really didn't want to say that. I really wanted to get to the end of this video and have a glowing appreciation or something for this steel. I don't think it's the steel. There could be a number of things. I'm not going to assume it's the steel. But the edge retention on this is already not even close to like the 5200 high carbon steel that I usually use. There could be a minor issue with the heat treat. Maybe my hardness target needs to be, maybe I need to do the heat treat differently, a higher austenitizing temperature. Maybe the quench didn't go as well as it should have. Maybe the plates didn't contact the steel and quench the steel as well as it should have, quickly as it should have. maybe there's more decarb on this blade than I realize. And maybe after sharpening it back a few times, we'll get down into some better steel. Maybe I didn't grind off enough steel to remove all the decarb after forging the blade. I don't want to leave this like this. Thinking back over it, you know, what is it? What could it be? I feel like it's probably the decarb issue. Probably we had more decarb in this steel than I removed. I don't know how bad this steel decarbs, because that's the other thing too. Some steels decarb way worse than others. 80 Sierra V2, that steel to date is the worst steel for decarb that I've ever worked with. But maybe this is somewhere in that range. I don't know. And then, you know, this blade had some discoloration, unlike the other one. It's possible that my foil packet failed a little bit on this particular blade too. I didn't get it sealed up all the way. There's just so many variables. That's why you have to test this stuff out. That's why you have to develop dependable processes for a specific product, for a specific steel, a specific design. And so that's what I'm doing here. Like, I've made hundreds and hundreds of knives, but I've never made knives out of MagnaCut before. And so I'm not just gonna assume that I can grind it out, throw it in the kiln, and, you know, immediately have a top quality product. And that's what I'm trying to do here, is turn out a top quality product. Because this knife right here, actually this is already seeming better right now. I think the decarb was probably our issue here. But anyway, this knife is better than probably 75% of the knives out there that you could get today. But that's not good enough. I want it to be in the top. For what it is, I want it to be in like the top 10%, 5%, right? That's what I'm going for. Okay, got a fresh cup of coffee, French roast. Back at it here. So I will say that I feel like after the second sharpening here, it's already doing better than it did on the first one. And I think that's the case. And so I'm gonna keep going until I feel like the edge is not very good. But right now it's still, like, it's already doing better than it did on the first go round. And so let's keep going here. I think that was our problem. I really hope, but I think the decarb on the edge side of the blade was the issue. So we're gonna keep going on this. Here's the thing, guys, like, I could edit all that out. And if I just whittled some more wood here, carved some more wood here, and sharpened it a couple times and figured that out and not put that in the video, you know, I mean, you don't put everything in the video, but this is, I mean, you guys are getting the real scoop here, the real world play-by-play. And that's something when you do videos, even things that you're working through, little issues, even more minor than this one, and you after you've personally worked through it and it's no longer a question or a dilemma, once you get to the editing stage of your video, sometimes it's you don't even think about, you just skip over it. So what I try to do is just remember that whoever's, you know, you guys watching did not go through that thought process, or just the process of solving the particular issue. And so sometimes you have to remember, because you've already gotten past it, right? But kind of remembering it from the viewer's perspective, you know, including the, just remembering to include the steps to the solution or the resolution of the problem in the video for the sake of the viewer. And sometimes that can get, you know, laborious, and if you literally included every moment that was spent trying to figure out a particular issue, it could be, you know, excessive and just make for a poor video, a bad video, you know, so you have to be cognizant of that too. So I'm just rambling as I'm carving on this, but the point I'm trying to make is I got a little scared there. I'm feeling a little less scared now. After this second sharpening, I'm feeling pretty good about the fact that it's probably just a layer of decarb on this blade, especially, I mean, this blade being forged as we did. So that makes me, I'm cautiously optimistic that that's all it was. But that first go out of the gate was disappointing, and you guys got to hear my thoughts just a few minutes after that happened, and now we're pressing forward, like I said. So this will be third sharpening here. I don't need to sharpen it though, is the problem. I really should keep going, because it's it'll still take hair off. It's not like as keen as it, you know, could be, but it's still totally serviceable. So I guess I should keep going, but I really feel pretty good about it at this point. I'm not gonna bore you guys with the many minutes here that I'm gonna be doing this. So I'm gonna turn the camera off here in a second and keep going, but I'll, you know, turn it back on here in a little bit. I feel like towards the tip of the blade here could stand for a little more material removal. This portion of the blade here is doing really well now, but I think there's probably a little more decarb effect up here. So I'm just gonna profile that back a little bit more here on the coarse side of the stone, like I did with the whole edge a little bit ago. And yeah, so, you know, running into issues in knife making, or anything else for that matter, is just part of the process. The real issue is, you know, if you can't figure out what caused the problem, that's when you have a problem. So if it wasn't just a layer of decarb giving us these issues, I would have to go back to the previous steps and figure out where something went wrong. I was trying to think of that earlier, you know, and I just couldn't think of what really could have gone wrong. And you know, you always go with the most obvious thing first and eliminate that as a possible problem. So I mean, that's what you guys are getting to see in real time. Actually, let me see if I can show you this. I don't know if I can get it on camera here. But you see the forged or mill finish right here on the flat of the blade, and then you see the silver colored steel here, but look in between that. There's this 16th inch wide, maybe a little wider, gray sort of stripe there in between the dark color and the clean steel. And that is decarb. That is decarb steel. And if you get it in just the right light, it's on both sides here, you'll see sort of a funny transition from the decarbed soft steel to the clean and hard steel. You can't probably see it in the camera, but it's sort of a wobbly, wavy line where it's gets into the hard steel. That's how thick the decarb is on this, and that makes sense. It's wider because it's at an angle, but it's still significant. Well guys, I think we got her figured out here. I've been end grain whittling this wood here for, I don't know, 10, 15, 20 minutes. A little while. I feel like I could keep going for a long time because it's still very sharp. It'll still pop a hair off. See that? So it's not getting dull. It's just holding the edge. It's doing really good now. Alright guys, well maybe the biggest takeaway from this video is going to be to be aware of decarb, which we all know about, right? But hey, that's a real example of how it can affect your finished product. So again, this is why we test stuff, this is why we, you know, figure stuff out before we just jump in. And I am excited to continue using this little blade here and keep putting it through the paces, but I am happy and excited to be able to give a positive initial, well, almost initial response to the steel and how it turned out with our heat treat. So I'm going to send the other one up to Alaska and get some feedback from the bush up there and keep working on using this one for carving, etc., etc. So as always, I appreciate you guys watching. I hope this video was helpful, and we'll see you on the next video.